I think I need to be allowed to share my screen here. Okay, please change the setting first, Pak Owen.
Okay.
Okay.
Sorry.
Okay, so yeah, we okay. Can you see my presented slide?
Yes, sir.
Anyone? Okay, so let's start with non-Newtonian fluids. Okay. Okay. Good morning, everyone. Okay. Hopefully, you guys are in good shape today. Okay. Whether you have taken morning bath or not, or whether you have done your exercise in the morning or not, but I think it's better for us to learn. Okay, to have our learning process in very comfortable way, in very fun way. Okay, in very delightful way. I mean, in very joyful way. So hope you guys can enjoy today's class. Okay, so what's the scope of today's lecture? Actually, non-Newtonian and Newtonian, their difference is only located at their apparent viscosity. So slightly, I will review kind of viscosity concept in Newtonian fluids, and then correction for power required to flow of non-Newtonian fluids. So in the end, we need to achieve the desired outcome. So you guys are our desired outcome here is for students to be capable of recognizing the difference between Newtonian and Newtonian fluid, okay, especially for the incompressible one. So don't think about non-Newtonian in compressible fluid. So it's going to be very complicated. It's not for you, undergraduate student. So that proper correction for power loss calculation in non-Newtonian fluids can be applied. Okay, yeah, or at least can be estimated. Okay. So I'm gonna review a little bit about viscosity. So you guys must remember this one, okay? Newtonian, dilatant, pseudoplastic, Bingham pseudoplastic, and you get this one. So in any case of fluids movement, okay, you always have the thing that is called the shear stress, okay? And then you will have the thing that is called as shear rate, okay? So this one is sorry, it's like this. Okay. This is the shear stress, and this one is the shear rate, and this one is called the viscosity. So what is the unit of the viscosity? Mu is equal to what? What is the unit of the viscosity? Can you guys mention it? Huh? What is the unit of viscosity? I think you guys have seen this in the opening of our class in fluid mechanics. Nobody? So the unit of viscosity is what? Pascal second, isn't it? Yes, Pascal second. This is the international system, the SI. Okay. So the unit of shear stress, sorry, of shear rate is 1/second. So what is the unit of the shear stress? So what is the unit of the shear stress? What is this? If the shear rate, people always call it dV per dr, or maybe sometimes it's called as gamma. Sorry, I'm not sure why my Wacom is not working well these days. Okay. Okay, gamma, or this one. Okay, the unit is 1/second. Okay, so what is the unit of the tau of the shear stress? Can you guys help me? Come on, you need to be more attentive in here. No,
Meter squared.
yeah, what?
Is it Newton per meter squared?
Yeah, so what is the Newton per meter square? What is the Pascal, isn't it? So when you are stressed, okay, if you still difficult to memorize the unit, you can stress. So when you are feeling stressed, you are feeling pressurized, okay? So what is the unit of the pressurized? Okay, this is Pascal, okay? So that's the easy thing. Okay, okay, let me clean up my scribble. So yeah, when you are moving the fluids, okay, there will be always shear stress and always shear rate, okay. Shear stress is usually given by you, okay, then shear rate is there, okay, it's the movement of the liquid. For the Newtonian, it's linear. I mean, for any shear rate, for any shear stress, the increase of shear rate, okay, for any delta tau, okay, the increase of delta gamma or maybe delta dV per dr is going to be constant, okay. You are increasing shear stress by 1, so a factor of just constant, and then maybe constant multiplied by 1 here. You increase this 2, then this is constant multiplied by 2, okay. Okay, that's this constant is called as viscosity, this one. But unfortunately, this word does not consist only Newtonian fluids, okay. Mostly for engineering, you will deal with a lot of non-Newtonian fluids. So yeah, you need to count for mu inconsistency for any given shear stress. Okay, so this is the non-Newtonian fluids. Let me group it a little bit. Okay. Yes.
We actually can't see what you're drawing or scribbling.
Oh, sorry. Let me share. Okay, let me share. Sorry. Okay. Oh, where is my Zoom? Okay. Oh. Share. Let me the screen to. Okay, share. Okay. Okay. Can you guys see my circle?
Yes, sir.
Okay. Yes. Good. Okay. Okay. So for non-Newtonian fluids. Okay. This thing, okay, this mu is not constant anymore. So when you give the pressure, okay, so shear stress can be resulted from the pressure, can be resulted from the movement of the fluid movers part, kind of the rotor of your pump or the piston. So it's there. The unit is Pascal. It symbolizes, it depicts the energy given to the system, to your fluid system. Okay, when you are giving the energy, okay, when you are giving the energy for any non-Newtonian fluids, when it's increasing, the shear rate is not equal anymore. The increase of the shear rate is not constant anymore. That's the thing. So this is quite tricky, but don't complicate the things. Okay, so only this thing is problematic. Okay, so I give you this note. So magnitude of effective resistance is not always same for every shear rate given. And then for Bingham fluids, okay, minimum shear stress or tau zero or tau yield stress has to be overcome. Has to be you must fight this thing first in order to move these fluids. Okay, so when you are using the toothpaste, okay, can you just flow your toothpaste? No, you cannot. Okay, in order to flow your toothpaste, you need to give initial energy. Okay, initial pressure. That's called the Bingham fluids, and this one is the most difficult thing to calculate. Bingham pseudoplastic. I'm not No, I don't think any lecturer in undergraduate study will give this as the exam, but at least you need to know that Bingham can also be Bingham Newtonian and Bingham pseudoplastic. I mean, why it is called Bingham? Because there is a tau yield here, or tau zero, or something else. I mean, a certain limit. I mean, a certain amount of energy must be given. Okay, so yeah, the example is the toothpaste. Okay, so yeah, sometimes we call this as apparent viscosity, but later on we will see. Okay, so during our shear stress application time, okay, shear stress period, for Newtonian, we also observed that during its operation, the fluid's viscosity is not going to change. So, yeah. But you can see here, for non-Newtonian, there are also two types. Okay, rheopectic and thixotropic. Sometimes when we are mixing some types of fluids, okay, it becomes more viscous, and it can also become less viscous. Okay, I'm not sure when you are mixing the paint with thinner. Okay, paint plus thinner. Have you ever painted your house or your cupboard? Have you guys?
Yes, sir.
Okay. When you are mixing the paint with thinner at the initial, it's kind of very viscous, but later on, when you are mixing it kind of longer, okay, it's gonna be less viscous. It's called isotropic. And for the opposite is the glue. Okay, glue plus its solvent. I'm not sure, but when you are mixing the glue with the solvent, at some time its viscosity is going to be increased, okay, because the molecule, yeah, inside the glue is gonna find its best linkage to each other. So yeah, so you need to think when you are operating when you are supposed trying to build a factory of glue, okay, glue industry. So you cannot use centrifugal pump, or your timing must be calculated correctly. Okay, you cannot you cannot just okay, I will mix my glue for 72 hours in that tank. So if you are mixing that thing inside that tank, I can guarantee that your tank will be solidified. Okay, the inside of the tank will be solidified because the glue has its kind of, I can say, it's gluing time. It's time to be more viscous. Okay, you need to think about this one. So, but Newtonian, when you are fixing water, either it is 1 hour, 1 year, 100 years, the viscosity is going to be the same. Okay. Okay. So yeah. Example of non-Newtonian fluids. So we have Newtonian, water, fruit juice, honey. Okay, honey is categorized as Newtonian. I almost couldn't believe it by myself, but honey is non-Newtonian. Sorry, it's Newtonian, although its viscosity is quite high. Okay, vegetable oils. And for pseudoplastic and dilatant, apple puree, maybe you guys like to watch MasterChef or whatsoever. I don't know the difference between puree, juice, ketchup, or whatsoever. So, but it's called apple puree. Okay, and then dilatant for shear thickening. Okay, cornstarch suspension. Okay, for Bingham, toothpaste, tomato ketchup. When you are maybe when you are eating at the tukang bakso, okay, you always see kind of what can I say, adult woman in Indonesian is called the mak-mak. Okay, they always like to eat a lot of ketchup. You can see their effort to add several tens of milliliters ketchup into their bowls of baso. Okay, they need to do they need to do exercise because tomato ketchup is categorized as Bingham. Okay, okay. Sorry. Okay. So any lesson from above mentioned table? Okay, I think you need to see that this is the lesson. Okay, Newtonian is water can be categorized as Newtonian. Fruit puree or fruit juice can be categorized as power number or dilatant or pseudoplastic. Okay, fruit jam can be categorized as Bingham. So can you take any lesson from this fact? Okay, from this phenomenon, can you take any lesson in here? Sorry guys, I cannot see your name. Okay. Can you take any lesson from this fact? No. Okay, because we have several slides in here, I need to cut the time. So increase of solid content causes the fluids to be less Newtonian. Okay, when you add more solid, its fluidity, okay, becoming less and less. I mean, very fluid one is always the Newtonian. You want to the water, pure water is Newtonian. But when you add the juice, okay, it's becoming less Newtonian. Means when you are giving the shear stress, when you are giving the pressure, it doesn't always follow your pressure. I mean, the flow rate does not always follow the pressure. Okay, when you are adding more and more, it's becoming Bingham. Okay, you need somehow to give the initial pressure to flow the fluids. Okay, that's the fact. So when you are, suppose you are designing tomato ketchup industrial scale or tomato ketchup chemical plant, I mean something like that, it's better for you. Okay, you don't just mix water with tomato in one pipe. It's gonna be difficult. I think you need to have special pipe for tomato, something like that. Okay, because when you are flowing these fluids, okay, when you are flowing Bingham fluids especially, you cannot use centrifugal pump. It's going to be there. Your pump is going to be overheat, or your pump is going to be rotating, but the flow is not there. I mean, it's just rotating aimlessly. I mean, but no flow can be detected because it cannot be used to flow the non-Newtonian fluids, especially for the Bingham fluids. But when you are using Bingham fluids, it's better for you to use positive displacement pump. Okay, to use piston pump. Okay, because the head is to be ensured with the piston movement compared to the rotation movement. Okay, I think you guys have learned about the pump type, haven't you?
Yes, sir. We did.
Okay, so yeah, never use centrifugal pump for Bingham especially. Okay, I will give you this video. I'm not sure. Can you guys hear the video? Can you guys hear the video? No?
I don't think we can, sir.
Okay, I'm not sure how to share computer sound. Okay.
Digital lesson.
Can you guys hear it?
Yes,
Today,
yes, sir.
Okay.
we're going to take on the interesting topic of Newtonian and non-Newtonian fluids. A classic Newtonian fluid is water. Water has a very predictable viscosity. and will always flow predictably regardless of the forces acting on it. Newtonian fluids also have predictable viscosity changes in response to temperature and pressure changes. To investigate the properties of Newtonian fluids experimentally, let's start with some warm honey. As you can see here, warm honey flows easily, and it will easily flow around objects, such as this ruler. Placing a force on the honey has no effect on its viscosity. Even if we place a large force on it with a hammer, the honey predictably flows around the hammer. If we try the same thing with cold honey, we see, as you would expect, the honey is more viscous. That is, it flows slower. But when we test it with the ruler, we see it behaves much like the warm honey. It's the same when using the hammer. Applying a force has no effect on the viscosity. Honey, whether it's warm or cold, is a good example of a Newtonian fluid. Let's try a different fluid. We'll perform the same test with cornstarch solution. When you pour this solution, it appears to behave much the same way as the honey. When you place a ruler into it slowly, the fluid flows around the ruler. However, when you attempt to force the ruler into the fluid instantly becomes more viscous. Hammering the fluid with even more force produces even more resistance to flow. Because a cornstarch solution's viscosity changes with an applied force, it is a non-Newtonian fluid. Unlike a Newtonian fluid, applying forces to this non-Newtonian fluid causes its particles to behave more like a solid. This makes the behavior of non-Newtonian fluids very strange. As you can see here, even though cornstarch solution flows when emptied from a bucket, you can't break its surface even when using a sledgehammer. You can even jump on and off a cornstarch solution. Just remember, don't stand on it, as you will eventually sink. So in summary, non-Newtonian fluids have unpredictable responses to applied forces. With applied forces, they become more viscous, such as cornstarch, or less viscous, like ketchup. What other fluids might you suspect to be non-Newtonian fluids? Try your own fluid experiments to find out. Thanks for viewing this Science Man digital lesson.
Okay, so you guys have had the lessons, I think. So when we are applying force in non-Newtonian fluids, it just cannot be predicted. Okay, sometimes it's getting harder, sometimes it's getting less harder, because when we are flowing the particle, okay, I think you guys have studied the particle flows, okay. When we are flowing the solid, okay, inside the fluids, the properties of that mixture cannot be regarded as fully fluid properties anymore, especially for these non-Newtonian fluids, okay. So when the solid content is increased, so it's becoming less predictable. Okay, so I'm gonna mention this assignment, okay. I'm going to need you to answer. For any incompressible fluids, more viscous apparent does always indicate for its non-Newtonian properties. Is it correct or not? Is it correct or not? Is this statement correct or not? Nobody?
No, sir.
No, why no?
Because some fluid becomes less viscous, or
Yeah, I mean, yeah, that's correct, but your answer is still quite far from this the reason. So suppose we have this tau, this is the gamma, okay? If we have Newtonian fluids, it doesn't matter whether you have this type of viscosity or this type of viscosity. As long the viscosity is predictable for any given tau, so you have the given shear rate, sorry, yeah. So mu1, you have mu2, mu1 is bigger than mu2, okay. So this one is still regarded as Newtonian, as you've seen before. The honey, okay, cold honey, okay, has high viscosity. It's very viscous, but its behavior is quite predictable. Okay. That's the reason why we cannot just say, okay, non-Newtonian fluid is the viscous fluids. No, it's wrong. Okay, that's not good. Okay. And then find examples for non-Newtonian fluids used in our daily activities. Find it by yourself, okay? Okay, so viscosity measurement of aspect. So this one, okay? So when you are dealing with Newtonian, the viscosity can also be predicted like this, okay? You can use the viscometer Oswald, viscometer Cannon-Fenske. I mean, the viscometer that uses the gravity to. Have you ever seen viscometer? At least in the Google? Yeah, usually viscometer is like this, kind of U pipe, so it's big and then big like this, okay? And then here we have the trajectory for the fluid. But for power law and Bingham, we cannot use that because some external forces must be measured. And in power law and Bingham, okay, sorry, for power law, we don't call it as viscosity anymore, okay? We call it as K. It's not apparent viscosity, but it's called as K. I mean, it's like viscosity. The unit is similar with viscosity, but the unit is not the Pascal second. Here we have the Pascal second. Here the unit is Pascal second minus N, okay? Minus N, hopefully. Sorry, I made a mistake. Pascal second exponent by N, okay? Because it's gonna be 1. Okay, it cancels this item. Okay, so we cannot just call it as the viscosity anymore. Okay, but the equipment will call it as viscosity. But later on, I will give you the example. Okay, so you don't get confused. For the Bingham, okay, actually Bingham, there are two Binghams. Okay, Bingham that follows Newtonian after it's given the required tau yield, and the other one is tau equal to tau 0 plus k dv per dr. Okay, explained by. So yeah, this is the Bingham pseudoplastic. So yeah, sometimes Bingham is like this, sometimes Bingham is like this. Okay, so that's for the second one, the calculation is not going to be easy. So we limit Bingham to the Bingham Newtonian. Okay, and let's discuss the Newtonian fluids viscosity measurement. You still remember the Hagen-Poiseuille equation, okay, for horizontal pipe. So they are measuring the Q, then they get the viscosity. Okay, this delta P is measured as the constant. Okay, and here you can see this one is equal to tau, isn't it? The unit is Pascal, and this one is equal, not that equal, but it's somehow similar to shear rate. Okay, this is meter cubic per second, isn't it? So yeah, that's the idea of viscometer. But sorry, I have a typo here. If in any certain increment of p minus p2, the Q is found to be linearly increased, okay, measured fluid can be categorized as Newtonian fluids. That's the Newtonian fluids. But if we have non-Newtonian, however, for this case, okay, somehow, okay, when we are giving different delta P, I can call it as delta P. the Q is not linearly increased. Okay, so we can have different apparent viscosity for any different delta P. So it's called as non-Newtonian fluids. Okay, and for the Bingham one, we always need the initial. So I give you the P unit because somehow you guys are more comfortable with P. Okay, I give you tau. Tau is gonna be you're gonna be. I mean, you're gonna be not quite comfortable. Okay, but later on I will go back to the tau. Okay, and for the measurement of the non-Newtonian fluids viscosity, we always use the equipment called as rheometer. Okay, it's not usual viscometer. Usually there are two types. Okay, this one is for the rotary one. We have kind of concentric rotator here, and here is the vessel of the fluids. I give you the different color here, and the fluid is kept in this slit. Okay, and then they are turning it. Okay, then they measure the tau from here, and then they also measure the gamma, or we call it as the dV per dr here. Then they get it. Okay, and the other type is this one. It's kind of, what can I say here? It's like syringe. Okay, okay, they give the delta P here. Okay, so they measure the gamma in here. Okay, for Newtonian fluids and non-Newtonian fluids, these two viscometer can be used quite universally. Okay, but for the previously mentioned viscosity, kind of the Cannon-Vanske Oswald viscometer, it's like you pipe like this. Okay, it's only good for Newtonian. Okay, because non-Newtonian, for non-Newtonian, suppose if it can give you the apparent viscosity, you can only get the viscosity of the fluids as the average viscosity. So the mu is not accurate anymore. Okay, especially for the Bingham, you cannot, because you need to push it here. Okay, so when in the future, okay, you maybe suppose you are taking your graduate study, okay, master or PhD, and when you are asked by your advisor, okay, now you are making this new polymer, please measure its viscosity with this viscometer, Oswald or Cannon-Vanske or Oberhold. Okay, please state that it's not correct. Okay, you need to use rotary rheometer in here. Okay, okay, you guys can still follow me, hopefully. Okay, okay, so pressure loss estimation for non-Newtonian fluids. So yeah, when you are dealing with Bernoulli, these things always there. Okay, you are happy when you see this thing, I believe, but it's not that easy anymore because the Reynolds is not like this anymore. Okay, this one is not equal with K. Okay, so you need to take the account for non-Newtonian fluids correction. Okay, whatever it is. Okay, okay. So for the dilatant or pseudoplastic-Laminar, okay, we can estimate this by using this equation and this one. Okay, it's very similar with Hagen-Poiseuille, isn't it? I mean, only the difference thing is it's not mu, it's K, but it's there. Okay, delta P is delta P, and it contains 1/n. When you are asking me, sir, excuse me, when where did you get this equation? So they got this equation based on experimental. Okay, they could not derive it easily, so they use, because for any non-Newtonian fluids, the pattern is not like this. Okay, like this, like I said to you before. For non-Newtonian fluids, the pattern is, I'm not sure, maybe like this, and suddenly stop like this. I mean, it's not same. I mean, it's not predictable anymore. Okay, this is, please don't be panic. Okay, this is just for the I mean, this slide is only for showing you that basically Hagen-Poiseuille equation is having its compatriot, it's similar, okay, similar brother or sister for non-Newtonian flow estimation. Okay, so yeah, so we cannot use the viscometer anymore sorry, we cannot use the U-type viscometer anymore due to this fact. Okay, I'm just showing you, so that is because I want you to know this one. Okay, so how about pressure loss estimation? Okay, so it's still same for the Reynolds, for the laminar one, but for the Reynolds is I'm sorry, for the fanning, I'm sorry, I slipped my tongue. For the fanning, for laminar is still the same, but for the Reynolds is not rho like this anymore. Okay, because you need to account for the non-Newtonianity. Okay, so this is the Reynolds of the non-Newtonian. Sometimes people just writing another like this, 2 n. Okay, something like this. This one. Okay, so it's not quite different actually. I mean, this one is to expand by 3, isn't it? Okay, so yeah, this is the correction for the Reynolds. So Reynolds for this is for the pseudoplastic and dilatant. I call it later as the power number. Okay, power number is this one. Okay, but this one is Bingham. Okay. Let me clear it for a while. Okay, for any rheometer, okay, they are not gonna give you, hey, I give you K. No, like it's not like that. For any rheometer, the data is the apparent viscosity at certain shear rate. Sometimes it's like that. So you need to take the calculation of K like this. Okay. There are two important relationships in here. Okay, this one is the basic relationship, and this one for the measurement relationship. Okay, so mu equal to minus K gamma exponent by n minus 1. Okay, later on we will use it. Okay, okay, for the fanning friction for the turbulent ones, until this time there is no equation that perfectly depicts the relationship of fanning friction factor with Reynolds number. Okay, yeah, that's in there. So usually when what should we do when we are measuring the delta P or anything else due to friction? Okay, usually we check the Reynolds and what else? We check the fanning, then what else? We use the Bernoulli, isn't it? Okay, the step is always like this. I show you. Fluid mechanics is not that difficult. Okay, the step is always like this. Okay, now we are stepping to the Bingham. Okay, Bingham laminar or Bingham turbulent. I just step it to Bingham turbulent because Bingham laminar is going to be pretty much same. Okay, there is certain non-dimensional number. So in the Bingham, okay, the fanning friction factor is the function of the Reynolds, but okay, it's not just Reynolds. We call there is a new dimensionless number. It's called the Hedstrom number. Okay, Hedstrom number is like this. Okay, you can the Hedstrom number depicts the relationship between the apparent viscosity and its initial, sorry, the tau yield. Okay. Unlike the Newtonian, for the Bingham, the graph is gonna be like this. Okay, so it's always the same. Okay, for the Bingham, you always measure Reynolds first, then you measure the fanning, then you, but the fanning cannot be measured directly. You must also measure the Hedstrom number. Then you go back here, use the Bernoulli. Okay, so it's gonna be the same like this. It's pretty much same. Okay. I'm not gonna explain this one because you guys are gonna be okay. I'm not gonna explain this one because this equation is kind of complicated for our limited time. Okay, so I'm just gonna give you the fact of non-Newtonian fluids delta P measurement. You are not gonna get mu is equal to what? No, it's not like this. The rheometer data, okay, rheometer data is always like this. Okay, how much the tau, then how much the shear rate, then you can get, this is the calculated one. Okay, because when you are having like this, okay, this is the tau, this is the gamma, it's like this. Okay, so the slope in here is the mu. Okay, the machine does not know it. Okay, as another mu. Okay, the machine did not know about its non-linearity. Seriously, it does not know how. So it just gives you the mu apparent for any given tau. Okay, so this one is measured, this one is measured, this one is calculated. Okay, I will step to the closing statement for this slide. Okay, I still have one more slide. All complicated calculations are used to account for the change of apparent viscosity, and all of those data were acquired from rheometer. Okay, so this is the step for non-Newtonian. You have the data shear rate versus shear stress, and then you get the corrected viscosity. Then you can just correct the pressure loss or flow rate calculation. That's all. Okay, it happens for two phases. It happens for liquid phases. Okay, actually for the liquid phases, it's simple. You get the mu. Okay, but what about for the non-Newtonian one? Okay, okay. I close this slide. Okay, I'm gonna show you another slide. Okay, sorry. I'm closing this slide. Oh, sorry. Oops. Discard, and then I will substitute. I will show you another exercise. Okay. Okay. Now you guys can see my shared slide. Hello. You guys can see this slide now?
Yes, sir.
Okay. So this is the example of the calculation. Okay. I have searched for many examples calculations so that you can get quite easy one. Okay. So this is non-Newtonian calculation example. Okay. You have the slurry of coal and then inside a horizontal pipeline. This is 8-inch schedule 40, so you can find it, what is the cross-sectional area at 80 kilometers. Okay, its volumetric flow rate is 0.06 meter cubic per second. Then of this fluid is categorized as pseudoplastic non-Newtonian fluid with flow behavior index. Okay, if you have tau equal to k gamma expanded by n, this is called as the flow behavior index. Okay, for the Newtonian one, the flow behavior index is 1. Okay, but for the non-Newtonian is less or bigger than 1. Okay, then I give you the data. measured viscosity at shear rate equal to this one is 50 centipoise. So how about 200 per second? How about 50 per second? So we will estimate it later. And then its apparent specific gravity is 1.4. Then calculate first. A is pressure difference of pipe inlet and outlet, and B the power requirement to achieve the desired flow rate. So fluid mechanics is always situated in these two issues, okay? Issues of pressure difference and then issues of the power requirement. That's fluid mechanics for chemical engineering. So the answer step is always calculating the Reynolds number, okay? Like I said to you before, Reynolds, then you can get the F, and then you get the delta P later by using Bernoulli, okay? So easy, isn't it? It's easy, seriously easy. How about to calculate the Reynolds number? Okay, you have the Q, you need to have the A, okay? So you get U, you can calculate it by yourself, okay? Requires you calculate by Q per A for 8 inch schedule 40, okay? You can find it by tabulation. Then this one is not easy. You need to find the K. So I gave you the relationship before, okay? Mu is equal minus K dV per dr and minus 1, okay? This is, you can find this one. Then what is the mu here? This is 50 centipoise, okay? You can change it to the Pascal second. And this one is 100 per second, okay? Then you get the K. After that, you just put the equation in here. So Reynolds is equal 8 and 1,400. Then what is the U? 2 minus N. You get it from this step 1. Then step I, sorry. Then you have the diameter of pipe, schedule 40, you know it, okay? And then what else? K you get from this step I, okay? Step 2, you get it. And then 2, 3, you can, this is 0.4, okay? And then plus 1 per 0.4, then exponent 0.4. And you get the Reynolds. I have calculated by myself. Is around 7,945. It's categorized as turbulent 1. So what else if after we get the Reynolds? It's always easy. Okay, don't complicate your life. Okay, we have the Reynolds here, maybe around 8,000. Then what is the end here is 0.4, and then maybe the final friction factor is around 0.004 and 0.005. Then I get, okay, 0.0045. That's my estimation. Okay, for this problem, I don't find any equation to estimate the F by using the equation. Then I get the F. What else? Using this relationship, okay, the pipe is both connected to the atmosphere. Then what else? Horizontal, T equal. Then you get the F here. Then you measure it. Delta P is equal to what? So here, from my calculation, delta P is equal to 177 bar. Okay, it's quite big. And then the energy requirement is calculated. Simple, isn't it? And you have delta P, and then you calculate it by, you multiply by Q, then you get the W. It's the energy requirements around 1 million watt. Okay, around 1 megawatt. Okay. So it's gonna be extremely high. Okay, for pumping this coal slurry at 0.06 meter cubic per second for 80 kilometers pipeline, which is going to be hard. Okay, I need you to do this self-assignment. Okay, redo the calculation with fluid that has N equal to 0.2 and 1, and tabulate the results with the current exercise results. So you can see here, and then here you can see the delta P, you can see the W. Okay, you 0.2, to this calculation 0.4, and this one. What is. Okay, do this tabulation. Do yourself a favor, okay? Don't just wait for your lecture. Okay. Sorry, I still in bahasa. This example number 2. Gravel suspension can be categorized as Bingham fluid with tau yield equal to 4 Pascal and then mu 0. Test. They will be flown in the horizontal pipe 8-inch, schedule 40 at 82 meters same. Its flow rate is desired at 0.006 meter cubic per second. Calculate pressure difference and then power requirement. Still the same. Step 1 is still in Indonesia. Calculate headstrong number here. Headstrong number is 2.5 million, and then calculate the Reynolds numbers. I hope you guys have any curiosity why the Reynolds number is not the same with previously one. Okay, the Reynolds number is like this because the behavior is like this. Okay, after its tau yield is overcome, it's just becoming Newtonian fluids again. Okay, that's the Bingham fluid in this case. Okay, and I get the Reynolds, I get this one. So Reynolds is almost laminar, and then yeah, how to find this one? We have two ways in here. How to find fanning fraction? Now we know the Reynolds number in here around 5,000 something. Okay, 50,000 or 5,000. Yeah, around 5,000 something. And then we know the headstrong numbers. Yeah, 2 million. Okay, it's gonna be around here. So the friction factor is around 0.11. But another thing is just you can use this following equation. Okay, they are fitted this data. So F is equal to 10 Reynolds of Bingham plastic exponent minus 0.93. If you are asking me, sir, where did it come from? It came from the experimental. Okay, then A square like this, then you can get the fanning. Okay, that's fanning of this calculation is 0.007. Fanning of this calculation is 0.11. So we have around 40% difference. Anyway, any approach will cause a certain amount of error. And then you can use the Bernoulli equation here. I just write it like this to F over D. So yes, because it came from P rho equal to for F over D. Okay, and this is 2. Then it can go here. Rho. Then you can measure the delta P. Delta P is around 3.4 bar, and then energy requirement is just you can just multiply it. Okay. Now you have the self-assignment, redo the calculation with a fluid that has tau 0 equal to 1 and 10. Then tabulate the results with the current exercise results. Okay, you have the tau 0. Okay, you have the delta P, you have the W or work. Okay, you have this, what is, I think this one is 4. Okay, so this is 4. Okay, 4, 1, 4, 10. Okay. How much? Okay, do yourself some favors. Okay, because when you can do this exercise by yourself, I don't think any exam problem will be big issues for you. Okay, I believe today's explanation, I mean it's very compressed one. I'm sorry, the pace is very fast because this lecture is compressed. Actually, I give this in K02 in 2 lectures. Okay, and now I give you in 1 lecture. Furthermore, is 1 hour, 1 lecture. Okay. Any question? No question.
It's all good, sir.
It's all good. Okay. So I will give you this file maybe through Pak Wawan. Okay. So you can try it by yourself. Do yourselves favor, okay? After trying this self-assignment, I think you guys can get clear and firm basic of calculation in non-Newtonian fluids, okay? Okay, I think today's class, I think I can conclude this one, okay? The most different thing in the non-Newtonian fluid is located at its apparent viscosity, okay? Because the apparent viscosity is not always the same for any given external force. That's the non-Newtonian thing. Other than that, it's gonna be the same, okay, for any delta P measurement, for any power requirement measurement, it's gonna be the same, okay. Okay, Pak Awan, I think this class is concluded. I think the session is returned to you.
Okay, thank you, Pak Haryo. Okay, I think because the time is already up, and I think they will have an exam after this. Thank you so much for Pak Haryo and all the students. I remind you to fill up the daftar hadir in CX. Okay, thank you all. Good morning.